too. Okay, where's my little thing? Turn it around. Okay, so we were talking about how the various multiplicities affect graphs. So everything we did in 3.2 and 3.3 was building skills to help us create graphs of polynomials here. So this, if you have a multiplicity of 2, you will see the graph either come down from above and just boing, bounce right off the x-axis and head back the direction it came. Or if the graph happens to be below and it needs to approach that 0, it can come from below and boing, bounce off. Nickname is a bounce. The official mathematical terminology where one graph just touches another one, in this case the x-axis, at a single point, is it is tangent to that. You may have heard that term used in geometry. You may have had circles, and you may have had lines that were tangent to the circle. Does that sound familiar at all? Okay. If it doesn't sound familiar, here's the deal. Tangent means it only touches at that one single point, which happens to be called the point of tangency. Now, why am I making a big deal out of this? Because many of you have calculus in your future. It is going to be a huge, humongous part of what you do in the first half of Cal 1 is finding the equation of a line of tangency. So a line of tangency hits a curve in only one spot. You'll also work on secant lines, which might hit in 2 spots. So just a precursor to calculus. Let's say I have a curve that looks like that, and I want to draw a line that's tangent in spot, then that line would be looking something about like that. That's a line of tangency, only touches one spot. But if I wanted a secant line, okay, say that again. Okay, it would intersect at another spot, but it's only tangent to this point, okay? So it may intersect the graph somewhere else, but if you're asking for a line of tangency, you're only saying it is hitting this point, and that's, okay, I see what you're saying, but it's in a local neighborhood, so it's tangent at this point. Now, if the graph is just going on and on, you may cross it somewhere else. But a secant line would be a line where I pick 2 points on the graph, maybe here and here, and I create a line that intersects both of those points. So that's a secant line, and that is a tangent line. Okay, so hold on, I'll just let that clear up. Say your question again, because I was focusing on.
Is that our next one?
No. Something from calculus. I just wanted you to show where you'll hear the term tangent used in calculus. Okay, so this whole diagram, this is looking backwards to geometry over here, and this is looking forward to calculus. But all we're saying is, if you are bouncing off the x-axis and heading back in the other direction without crossing it, then you are tangent to the x-axis. Okay? You might want to hang on some of this stuff. You definitely need the toolkit that I'm filling up in your head to survive calculus. Oh, yeah, hang on to that. Might be useful. Okay, last situation, and then we're going to expand a little bit on this on the next page. If you have, so these two are odd multiplicities. A simple 1 goes straight across. A higher odd, 3, 5, 7, flattens out, but it crosses. Okay? An even multiplicity does not go across. It turns around and goes back in the direction you came from. But if you have a higher even number than 2, tell me the next few even numbers higher than 2.
4, 6, 8,
Then it is tangent meaning it's not crossing. It's just going to turn around unofficially. It bounces. Okay, that's the unofficial. It bounces and heads back the other direction, but it's tangent and it flattens out. So it's very hard. It's very hard to draw these. So as we turn the page, you're going to see where I let the computer graph some of this. But if I'm going to go tangent, here's a couple of features. If I'm starting at this point and I'm saying, hey, I got to get to that 0, but it has a multiplicity of 4. Watch what my graph's going to do. It's going to come in a little more steeply, and then it kind of flattens out and continues. That's a terrible drawing because drawing these higher even multiplicities is just hard. So knowing it is hard, there's not going to be any questions where you are responsible to draw a multiplicity higher than 3.
Do we need
Trust me. You do not need a calculator at this point, but we might. I'm not sure. If you need it, I'll tell you to run grab it. Okay, if you hadn't already gotten one anyway. And I went to, there's a website called Desmos where you can graph things. Okay, yeah, Desmos. I use Desmos to create these graphs.
So like, it's like that last one you just told us.
Mhm.
It's kind of like a pencil solver, how it curves and it flattens.
Yeah.
Look at it.
Yeah, so here's a better example. Here's a better example, okay? I have taken parent functions and I have graphed, this says f of x, I'm going to say y equals, I graphed y equals x squared right here. Can you kind of see? Originally, this was all colored, but I can't print in color, but can you see which one is the y equals x squared in the center? Looks like your classic parabola, right? But then I also graphed y equals x to the 4th, and then y equals x to the 6th. So I'm going to come down. I'm going to zoom in a little closer. All 3 of these graphs, so this is the parent quadratic. This is the parent quartic. Did you ever look up quintic? Okay. What would we call this? Parent hectic? Hectic? It's hectic to draw it. Sextet or sextic. I don't know. Nobody really uses terms beyond quadratic and cubic. Yeah, quartic, huh?
I think we do hextic or hectic.
Okay, yeah. Well, if I had to draw this, it would be very hectic. Because if you look at this, the power is the one that's coming in on the inside. It's coming in a little more steeply. It's flattening out. Is this meeting your eraser topper definition? Okay. The thing is, it totally looks like this curve is sitting on the x-axis for a very wide space, and it looks like it's constant for a while. Doesn't it look like that? It's not. It is only touching the x-axis at the 0. So why does it look like it's laying there? It's ridiculous tiny decimal or fraction numbers. Okay, super like 1/1,000,000. How big would 1/1,000,000 be? Tiny. You couldn't see the space. But the only place that any of these curves actually hit the x-axis is at the 0. That's important. So these are graphs of the form f of x equals x to the n, where n is greater than 2. Actually, or equal to 2, because I did give you x squared. These are all your even powers, right? And when you have an even power, do you cross the x-axis or do you bounce? Okay, but check the second picture. What's this the picture of? I did x cubed, which you're familiar with. It sort of flattens out at x cubed, doesn't it? Or x to the 5th, x to the 7th, it flattens out more. But once again, it is only hitting the x-axis at that one single point.
So you mentioned that when it comes to even ones, we only have one that's like 2. We would put for odd, obviously, we have like 5 and 7 still.
Odds would be just an odd exponent, like 5, 7. So that would be your
You
multiplicity.
said when it comes to like drawing, you have one higher.
You'll see it as we go into it. You will never be asked to draw these higher because they're crazy to draw. And you will never be asked to guess a higher multiplicity, okay? So if you're given a graph and you're trying to say, what's the multiplicity? If it bounces, it's going to be a square. You're going to see it bounce. You're not going to see it flatten out, and you have to guess, is it to the 4th or is it to the 6th? And if it crosses and flattens, it will be to the 3rd power. So you don't have to guess, is it to the 5th or to the 7th? Because you just can't. So we can't ask you something that you can't actually perform, okay? Now, what if I had included y equals x to the 1? That would have just been the straight line, the parent line, right? No curves to it at all.
You say you always like straight lines, where's your ruler?
Pretty straight line there. Not getting candy for that. We're just moving on. All right. So here, make you people happy. Oh, it wasn't perfectly straight. I stand corrected. Now I missed my zeros. I'm just gonna make the point a little bit bigger.
We have to draw straight lines.
You're right. I should set a better example. I have been chastened and I am repenting and pulled out my straight edge. Thank you for forcing me to set a better example for you. I love this class. Okay, I got a triple star in this particular note. We are going to be creating graphs. We are going to limit ourselves to what we worry about. So here's the deal, Lucille. When we make graphs in this section, we will not use a Y scale on our graphs. I've given you a couple of polynomial graphs just for you to get a picture, but they've used a Y scale, haven't they? They put numbers on their Y-axis, which forced them to make sure the curve was exactly right, okay? Over here, they put numbers on their X-axis and Y-axis, although on the X, they're counting by ones. What are they counting by on the Y's here? Okay, for the tick marks, it's by 5s. Good eye, okay? So we are not going to put any numbers on our Y-axis. So our graphs are not going to be exactly accurate. The features that will be correct will be our end behavior and our zeros and our crossings at the zeros. Sir?
You skipped the graphs polynomial.
No, I didn't. I just wanted to point out the finish my sentence here, okay? So there's an exception here. If you know the y-intercept and you would like to show that on your y-axis, you are welcome to do it. You would be able to easily know the y-intercept if your polynomial function, if your equation is in standard form, not factored. So if you look at this equation, y equals x to the, I think that's a 5th. I'm not even completely sure. Minus 8x to the 3rd. Now I'm completely sure it's a 5th. Plus a 10x plus a 6. Do you know what the y-intercept is if you just look at that?
No, but you figure it out.
Okay, listen to me. A y-intercept is an ordered pair that has a y value, but what's the x value for the y-intercept? If you have a point on the y-axis, what is the x value if you are on the y-axis? 0. So you guys, check out this graph that's going from low, high, really high, is this top graph. Where does it look like it's hitting the y-axis?
Around 6.
Around 6. Look at the equation.
6.
6 is the constant. What would happen if you plugged in a 0 for every one of these x values? What would survive?
6.
The 6. So if it is not factored, the constant is the y-intercept. If it is factored, you don't see that constant. Check out this equation. I know it's really tiny,
Like, in the blank.
but what's the constant on this one?
I can't read it.
Okay, I'm going to read it to you. It's x cubed
Zero.
minus 2x squared minus 3x, and it just stopped. What's the constant?
Zero.
Where does it hit the y-axis?
Zero.
Yeah, if there is no constant, your graph is crossing through the origin.
So standard form goes in the blank, right?
So, graphs of polynomials, no, actually no. The domain of a polynomial function is what? It's all real numbers, because in a polynomial function, x is never in the denominator and x is never under a square root. So we have no domain restrictions, all real numbers. They are continuous, smooth curves. There are 4 pieces of information that we can gather from the equation to help us in our graphing thing. First of all, end behavior. How do you find end behavior?
The highest one, the
The
highest.
leading term, but it needs to be unfactored to get end behavior, right? Okay. How do we find the zeros? That's what you did for homework last night, isn't it?
Nothing.
You may have used synthetic division. You may have used a calculator to assist you. Okay. But you were able to take a polynomial and find the zeros with synthetic division and factoring, right? We know that. On our graph, where will the zeros go on a graph? What do you think goes in these blanks? Zeros are also known as the x-intercepts. Now, that's if you have real zeros. If you have imaginary zeros, check this graph here. Do you see how it goes up, comes down like it's heading for the x-axis, but it never reaches the x-axis, and it decides to turn around and head back up again, and then comes down and hits the x-axis. Can you focus on this graph and ignore the one that kind of looks like a W for a moment? We have a real zero right there, crosses the x-axis or hits the x-axis, right? How many more real zeros do you see on this curve?
2.
There's one right there. There's one right there, right?
1.6.
Okay. That belongs to this top function. How many zeros does this function tell me I'm going to have? 5. But we're only crossing the x-axis 3 times. Well, let's check it out. Look at the zeros. How did it cross? Did that go straight across, or did it flatten out? Straight across. That's multiplicity of 1. What about this one? Multiplicity of 1. What about this one? Multiplicity of 1. So where are my other 2 zeros? If they're not real, they must be imaginary. Imaginary zeros will cause you to have a turnaround without hitting the x-axis. So if I look at a graph that has headed towards the x-axis, changed its mind, went off the other direction without going all the way to the x-axis, I can promise you some of your zeros are imaginary.
How do we put that?
Okay, well, I'm not going to ask you, but if I had asked you to find the zeros of this function, and you would use technology to assist you, you might have, well, these are kind of ugly zeros. This one, but at some point when you got it down to quadratic and you did the quadratic on your last 2 zeros, it would have been imaginary. You would have plus minus i's for the last 2 zeros. Okay. Now, other things we know are the multiplicities. So the multiplicities for the zero tell us how to cross. If you have a multiplicity of 1, what's your graph going to do when it gets to that 0? Go through it. If it's coming from above, it's going to go down. If it's coming from below, it's going to. Multiplicity of 2, what's it going to do when it gets there? Boing. What's it going to do with multiplicity of 3? Slow down and then kind of flatten out as it crosses. Okay. And then finally, the 4th one, if the equation is not is the y-intercept. It's also important to know if 0 is a 0, you are crossing at the origin. That means there is no constant there. All right, so let's play this. Okay, so work examples 29 through 45. Your instructions are to sketch the graph. Look at me, make eye contact with me. You have no idea what you're not near the x-axis except at the end. So these are sketches that give me a generalized shape, but they will only be accurate as far as the end behavior, where the zeros are located, and how we cross. Keep that in mind. I'll explain what that means as we work it. Look at this first equation. Is it given to me in factored form or unfactored form? If it is in factored form, then it means finding your zeros is super friendly. If it is already factored, you might want to note factored form, then these zeros are like being handed to you. Now, y'all, take a look at this very first thing that they factored out. Do you see how it has a monomial out in front?
2 zeros would be it.
Okay, if you have a monomial, that means that 0 is one of your zeros. But since that x is squared, what's its multiplicity? So I'm going to put multiplicity of 2, which tells me a little bit of something about what my graph is going to do at 0. Okay? Now, what other zeros do you see? 5, -3, and 1. I do not mention the multiplicity if it only happens once. If I just list it once, then you can assume it's a multiplicity of 1. So on my graph, I am going to put points at 5 and at -3, no particular order here, and at 0 and at 1. That only looks like 4 zeros. But my behavior when I approach that 0 will tell you if it had a multiplicity greater than 1. The next thing I need is my end behavior. I always write EB for the end behavior. About 3 years ago, I had a guy in my college algebra class, okay? Big, tall guy, redheaded, had a huge, great sense of humor. He slept in my class most of the time, and it made me mad. And I always thought, this is going to fail. But then he would manage to pull off a decent enough test grades that he always passed and he got credit. Drove me nuts. Okay? So anyway, he got the credit. Good for him. All right? So one day we were talking about end behavior. He was sound asleep. So I hollered his name and I said, hey, I can't remember his name. I can hardly remember y'all's name. He popped up. I did not say that. He popped up, looked at me with, sleepy eyes, and I said, what's EB stand for? Oh, then he thought about it and goes, Easter Bunny? No, it was not the Easter Bunny. But now I can't look at EB without thinking about Easter Bunny, and you can't unsee it and unhear it either. So it's not the Easter Bunny, it's the end behavior. But the end behavior needs the leading term when it is not factored. Our example is factored.
Do we need to,
How do we need to do what?
do we need to unfactor it?
If we had to unfactor it, we'd have to FOIL and then distribute that and then distribute that. So are you hoping maybe there's an easier way?
Hoping, but
Okay, so if it is unfactored, you can find the leading term by every leading term and its coefficients and its powers. So I have an x squared, okay? And don't worry, ignore all your constants, okay? because I wanted you to have candy. Help yourself. Okay, taking an x square. Then in this next term, I have an x, then I have an x, then I have another x. If you will multiply all the x's together, including any coefficients, do any of those x's happen to have a coefficient? Okay, all right. Include any coefficients, including any coefficients that might have been factored out as a GCF at the beginning, and including their powers. Well, these three x's were multiplicities of ones, right? If you will multiply those all together, you will have your leading term. So what would the leading term be if I multiplied all that, but I didn't want to mess with everything else? It would be what? X to the what? Fifth. That is the leading term. Now I have to tell you, look, if I had a -3 in front of this x squared, then I would have to multiply that -3 with it. Okay? So any GCFs that are factored out need to be part of it. Any x's and any multiplicity. So if this last one was an x cubed, I would have multiplied as an x cubed. Now tell me, give me an in behavior diagram for this. If I'm looking at the term x to the fifth, what is the right side of my graph going to be doing at the end? The right side of my graph is going to be curving up, okay? Because this is positive, and the left side is going to be doing the, okay, opposite because it's odd, right? Now, with those two pieces of information, but that's not this one. Okay. I got you. It didn't look like that from when I first started. Okay. Now, grab. I need you to have a pencil in your hand. I need to have a pencil in mine. Because you may decide to do a little bit of changing. You may be aiming for a particular zero, and you may accidentally totally miss it. And you just need to back up and erase it a little bit. Okay. I start with the x-intercept farthest to the left, okay? Now, these are my only intercepts. So to the left of this, at some point, my graph is going to be going down. And this is my farthest x-intercept on the right, correct? My farthest zero. So beyond this, it's going to be curving up. I expect if you are in a grid that you go off the edge of the grid with zeros on, oh no, with arrows on the end. So from this zero to the left of it, my graph is curving downward, isn't it? What is the behavior going to be at this value, which is -3? Okay, no, what's the behavior? What am I going to do at the -3? Okay, to the left of it's going to be down, to the right it's going to be above. How's it going to cross? Is it going to flatten, go straight across, or bounce? Okay, so aiming for this, I'm going to go a little to the left and down and pick some point to be going off the grid, and I'm going to start aiming for that zero. And when I get there, what am I going to do when I get to that first zero? Zip straight through it. Now, I'm just going to go a smidge. I don't want to go too far. I don't have any idea how high to go. I do not have any information about how high I want to go before it turns around. So you cannot get that part wrong. All you know is you are up above, and if you go very far, you're going to miss the next zero, aren't you? So at some point, you're going to have to turn around and aim for your next zero. So let's think about what's happening at the next zero. It's a boing. Why is it a boing? It's a multiplicity of 2. So I want to make sure that I'm going to come towards that zero and be able to bounce off of it. Well, I don't have very long to think, oh snap, there's another zero coming up real fast. I'm up above. My next zero is at 1. It has a multiplicity of 1. What's supposed to happen when I get to that next zero? Do I bounce again? Okay, so I don't have much room to turn around. before I cross again. Now I'm below.
And we have another zero.
Oh, there's another 0 coming up. I better turn around somewhere.
This is
All right, and aim. Oh, I need a plan. What am I going to do when I go through it? Get to it? Straight through it? And
How do you know how far down you are?
you don't. And that's the beauty of this. So, Emily, I'm going to show you what all different ways this could have looked and still been fine in just a second, okay? Now, at this point, what happens?
you go all the off the grid.
I just start going up and up and up and up forever. It never goes straight up because it's a function. All right? Now, I am going to raise this screen because I don't want to draw on the screen.
And you find that it bounced off that point, how,
Because when 0 was a 0, because that's my 0 at 0, it had a multiplicity of 2. So it's balanced. Now, some other kid drawing the exact same graph has those zeros, they have to have the same behavior. They may have started here and started up, and they may have gone way up and then said, I'm going to turn around and come here and bounce. And maybe they just wanted to bounce a little bit before they crossed here. Maybe they didn't want to go very far down at all, and they did that.
But they can also go super high.
Is that person right? That person is right. Let's find another marker. Okay? Maybe I have somebody who likes to go way up. Okay? Maybe they came in super steep. I think I may have gotten dysfunctional there for a moment.
You did. That was just a psycho though.
Okay?
Can we all draw our own?
And then they probably would need to use an eraser because that's really bad right there. But they also just erased Mr. Green guy. Okay? Mr. Green guy died.
Brent's a psycho. You went too hard.
Okay, so when I say there is no Y scale, you have no idea how high you're going and how low. So that's exactly right. You don't know it. But let's say you had a multiple choice question and you had created a graph like this and they had 4 graphs. If you find a graph that doesn't have the right end behavior, you go, well, that can't be it. If you find a graph that doesn't have the zeros in the right locations, then you go, that can't be it. If you have a graph that
Goes down.
bounced here and crossed there, you go, oh, those aren't the right crossings. So you have enough information to recognize a correct graph just from end behavior, location of the zeros, and the crossings or what you do at
What do
the
you mean when
zeros.
it bounces and should have zipped?
Okay?
Like if for like.
Yeah, like some kid, like some,
Show it the one in that 5. Let's say in this area to draw.
okay, so let's say somebody decided to come back here. Red, and they did that. Would that answer be okay? What's wrong with that? Wrong in behavior, okay? They did the wrong thing at that 0, didn't
Oh, I
they?
wish somebody was a bounce into a zip.
Huh?
That's so confused. I
Okay, so maybe somebody
red.
zipped across here, now they're down when they should be up, and then maybe they bounced there. Okay, so anyway, we are not looking for perfection. We are looking for a certain set of features to be correct. Those features are their multiplicities tell us, and your invalid. What this one really should look like.
What do we box on this one?
Hmm?
What do we box for the answer?
Look at that huge one. So the graph is the answer. So if you're drawing me a graph, probably don't even bother
Do you want
box it.
us to box zeros?
No, I am just going to check for the features on your graph. I am going to want to see that you thought about these. So your scratch work would need to tell me the zeros and to tell me the end behavior, but then your graph. And by the way, you're not copying it out of a calculator. So you must show me that you considered the zeros and that you wrote your end behavior. Now, if I were to type this guy into the calculator,
X squared.
okay, hang on, let me get my square now. What else we got?
X minus 5.
Blah, 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 blah. I'm so slow with this.
X plus 3.
+3 and
X plus minus
Plus or minus 1?
Minus.
Ah!
I'm 3 on 1.
Okay, now check out our version versus the calculator's version. Are you ready? By the way, the calculator is set up to the standard zoom, so it's got a 10, it goes out 10 in each direction. Here's their graph. Okay, so
That's exactly-
what matches ours? They started low,
we have-
they crossed at -3, they went way up, came down, bounced at 0,
Barely went up.
had to make a quick turnaround to get to the 1, crossed and went down, went way down. We have no idea how far down they went. Came back up at, is that 5?
It could be changing right after the extra behavior, it could be changing
Okay.
1,000 points.
Do they have the same correct information that we have? Do they have the correct end behavior? It's hard to tell what the end behavior is by just looking at the graph, so you have to know it. Did they bounce in the right places, cross in the right places, have zeros in the right places? Then my graph is just as good as theirs for our purposes. So let's try another one, okay? You with me? Okay.
This one comes-
Number 30 is in unfactored form.
Which means our end behavior is going to be really easy to get.
So let's just start with the end behavior. So it's like unfactored is great for end behavior, but not great for zeros. Factored is great for zeros, but you got to work for the end behavior. What am I going to use for my end behavior?
The x3.
The x cubed, and what does it tell me about the right side
Up to the right.
and left side? Down.
So it's gonna-
Same end behavior as last time. But now I need my zeros. Y'all, this is what you did last night. What did you have to do in order to find your zeros? And you may grab a calculator to assist you in this. But first, you will need your
We-
PRZ list, right? So if you're having to find the zeros, I want to see a PRZ list. What's going to be on top?
On top of P, which would be 15, which is going to be 1, 3, 5, 15.
And what's going to be on bottom?
1.
A 1. So pretty much possible rational zeros are positive and negative 1, 3, 5, 15. So how can that help you get started with your zeros?
Well, we can first put into the calculator the equation. that will solve
Okay.
the first one.
So we've got an x cubed plus a 3x squared minus 13x minus a 15. Okay, say that again. I'm still going to just be graphing. So for your PRZ, you just need it there as scratch work. And there's really nothing to box because it's a graph.
Do you want us, is it okay if we just box it for ourselves?
No, sure. Won't hurt me at all. It also, if it helps you or highlight your end behavior, these are all things that are going to help you get the graph. I'm carefully examining the graph, but expecting some scratch work other than you just graphed it.
Now we go to
Okay.
the second table.
So go to the table. I'm looking for, okay, 3. You see one at 3, you see one at -1, and you see one at, where else did you say? -5. Totally missed that guy. How many zeros should we have? Did the calculator give them all to you? Okay, so you don't really have to do the synthetic division if they're all there. So my zeros are at what location? And 3. So if they're not funky fractions and they're not imaginary, and you can account for all of them from the calculator, well, thank you, Mr. Calculator. The PRZ list at least kind of told me where to start looking in the calculator. Okay? So I also know one extra thing. I happen to know the y-intercept is located where? Okay? Well, this graph doesn't go to 15, but I don't have a scale. So here's what I do. I would not pick a point and say this is 15 because then you have to hit it. I would draw my graph, and when I'm finished with it, then I'd put a point and call it 15. Okay, so let's get our zeros in place. -5, -1, 3, putting a pencil in my hand, starting on the left. Where do I begin?
Down.
I'm coming from below, right? So, and I should have a plan before I aim for it. What am I gonna do when I get to the -5? Zip right through it. So I think this is a good place to start. Zipped right through it. I'll come down here and put my arrow on the end while I think about what happens next. What does happen next? Oh, and you know what? I lied. My y-intercept is not at 15.
Negative.
It's at -15 because I was starting to think, how the heck am I going to be at -15, positive 15? Okay, so I'm going to go up a little ways, however far I want, but at some point I need to start considering that I'm approaching another zero, so I need to turn around with a smooth curve and aim for it. And what am I going to do when I get there? Straight through it. My pencil's so sharp it doesn't want to make that turn. Shoo. Okay, it's time to make a decision.
Bulldoze the next one again.
Bulldoze. Okay, I need to turn around and start aiming for it.
Yeah, just spread there.
And then bulldoze, and then what?
Keep going.
Keep going.
And
Okay, if I wanted, I could take this point and call it -15. Probably need to write it big enough. You do not have to label your y-intercept unless you just want to.
You're looking at the zeros to figure out if what you're doing.
Say that again.
Looking at the zeros.
I'm looking at their multiplicities.
Is there any multiplicity?
Then it's a multiplicity of 1, you zip right through it.
What if it's like a multiplicity of 4?
Then I would bound. Okay, first of all, I'm never going to ask you to draw a graph with a multiplicity higher than 3. Okay, I promise. So if you're creating the graph, if this guy, let me pull this up so I can draw on it. Let's say that that guy, let's make a him. How about him? Use that, my 3. Let's say that my 3 had a multiplicity of 3, which means this would have been a much higher power, right? Then I did all this. La, 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 zip, la, la, zip, la, la, la. Oh, if I have a multiplicity of 3, I need to kind of flatten out like a cubic graph, right? So I'm going to come up a little to the left of it so I can flatten out before I zip. Now, from where you guys are sitting, is it obvious that I flattened out a little bit? You can see it. Okay.
We had,
Which, yeah, go ahead.
on our homework, we had ones like this, like when I was in the graph, I could not tell what they were, if we wanted to do this.
On the homework from,
This thing, because some of them are like, I was doing more than.
what, so are you looking at 3.4?
There was 3.3 in the category we had, I was looking at some of the other ones, like past. like,
Okay, but the graphing didn't start happening until 3.4, so apparently it wasn't a concern then. But we will catch this number 68, which is our last problem tomorrow. But take a quick look. How many zeros do you think this guy has?
3.
Okay, what do you think the power is? What's happening here?
That's a zip.
And that's a cube, so it's gonna be a polynomial to what power? 4, because we got 3 plus 1.
Is there a question on our cat food?
And besides, look, if you're in behavior, they're both going the same way, it has to be even, doesn't it?
I have a question on cat food.
Okay, on your cat quiz, I can answer. What is it?
On number 1, my mind was not me mapping, but I think I did it correctly. But you didn't have to go any further than you can do, right?
Okay, use synthetic criticism to decide whether it is a 0. So if you get a 0, it's a yes, okay?
Yes, and then I didn't have to go any further.
No. Yeah, so this was back before we learned how to keep going.
I'm making sure, because I mean, I was following my notes, but
Yeah. So, yeah, you just got to stop at, yes, it's a 0. And if it wasn't, then I would like for you to tell me f of 3 was equal to 8 with your math, okay? Let's stop this delicious video.